In this lab, we'll start using a new electrical component, the capacitor. Here are some capacitors stuck into some cardboard tape. We can pull them out to use them. There we go. There's lots of different sizes of capacitor, from the tiny picofarad to all the way up to the farad size. Normally we work in the microfarad size capacitor. So this is a 1 microfarad capacitor. This version is not polarized. You can usually tell because the legs are the same size, or there's not a plus sign written on the base that would indicate that one side is positive, or a stripe that would indicate that one side is negative. There are capacitors that are polarized, usually the larger sizes. So if you've got a 10 microfarad or more, you can look out for that. But typically, when we're using capacitors, they're on the small size, 1 microfarad or less. A capacitor varies from a resistor because it has a different constitutive equation. So for a resistor, we have Ohm's law, V equals IR. For a capacitor, we have V is equal to the integral of the current that goes through the resistor divided by its capacitance C. So the capacitance C has the units of farads. Of course, we're usually working in the microfarads area. And this means that initially, a capacitor with no charge on it will have no voltage across it. And as current goes through the capacitor, the voltage across it will increase. Now, how do we figure out the capacitance of one of these capacitors? You probably can't see it in the video here, but on the front of the capacitor are 3 numbers. I'm going to call them A, B, and C. So we have to turn those 3 numbers into the capacitive value, kind of like when we look at a resistor, we use the color bands to figure out what its resistance is. So for a capacitor, it's A, B times 10 to the C picofarads. So for instance, this one says 105, so it says 10 times 10 to the 5 picofarad. Okay, that means it's 10 to the 6 picofarad. A picofarad is 10 to the minus 12. So 10 to the 6 times 10 to the minus 12 means that this is a 10 to the minus 6 picofarad, or 1 microfarad. You'll notice the ones that I put in your kit, we have 105, 104, 103, 102, 101, and then what they call 10J, which is essentially 010. So we've got from 10 picofarads up to 1 microfarad capacitors. Now, when you draw a schematic of a capacitor, it's 2 parallel lines, because you can think of a capacitor as 2 parallel plates, and as current goes through the capacitor, we get a voltage across it, and it has a capacitance C. And in this case, we would write this is a 1 microfarad capacitor, 1 mu F. You would never write this is a 105 capacitor, even though the capacitor says 105 on it. That'd be like saying this is a brown, black, red resistor. We don't say that. We say it's a 1K resistor, and then we let whoever's reading the schematic find that capacitor. So just to reiterate, this is a 105. It actually says 105Z on it. We'll ignore the Z. I don't think it means anything. Then you also have a 104, 103, 102, 101, and a 10J. So that just means 100. So you should practice finding those in your kit. The text is real tiny, and making sure that you understand that a 104 is 10 times 10 to the 4 picofarads, which would be a 0.1 microfarad capacitor. So let's see, what do we do with this new element that has an integral within its equation? What does that mean? So just like a resistor, let's start off by building some kind of voltage divider circuit. So we'll have a resistor that's in series with a capacitor to ground. And we'll look at the voltage out, which is the same thing as saying the voltage across the capacitor. So the capacitor has some value C, and the resistor has some value R. And because the current that goes through the resistor is going to go through the capacitor, that current is going to charge up the capacitor. And now we have to think about how does this change with time? Because if the voltage across the capacitor is the integral of the current, if we wait a long time, so once this has charged up enough, this voltage out will eventually be whatever this voltage is here. So let's add another component here so that we can see how things change with time. Let's add a button. So we'll have, we'll just take 5 volts as our input, and we'll put a button from the 5 volts to the resistor. So in your kit, we've got some buttons. Find those. Here are some push buttons. I've got 2 also embedded in a piece of tape, and you can push them. This is essentially a wire that's broken, and when you push the plunger, it makes the connection between the 2 wires, making a connected wire. So when we're not pushing the button, this wire here is not connected to 5. When you push the button, it is connected to 5. That means current can flow this way, charging the capacitor. Note that these have some funny little feet on them so that they were able to stick in this piece of tape. So when you start to use these buttons, don't pull them out of the tape, because then those little feet, they get stuck in your breadboard. So instead, I always say cut your buttons out of the tape. This. And we're going to use 2 buttons in this circuit. We're going to have this first button that we're going to call the charge button. So when you push this button, it's going to charge the capacitor. But once you've charged this capacitor, what happens? All that charge is on the capacitor. There's a voltage across it. Unless you dissipate it somehow, that voltage should stay there forever, although it does self-dissipate a little bit, but it does it very slowly. So we're going to put another button here in parallel to the capacitor, and we're going to call this the discharge button, which is labeled dis. So what happens when you push this button? When you push that button, you're connecting the top of the capacitor to ground. So whatever voltage is across this capacitor, because there's charge on it, that charge will be instantly shoved into ground. So we're making a short. A short's normally bad, but there's not much capacity in this capacitor. So that that infinite amount of current when we close this button doesn't really do anything bad. If that was like a 1 farad capacitor, I'd be a little worried, and we'd probably stick a resistor somewhere like here, so that we don't make a short, and then we heat up this resistor. But for now, we'll just leave that as a wire. So we'll let this short. What do we expect to happen? So we've got the V out versus time. And let's say that nothing's happened for a very long time, that there's no charge on the capacitor, so the voltage is 0. Then at some point, we're going to push the charge button. So this is the charge event. What happens? Well, there's initially no voltage across the capacitor. So if the voltage across the capacitor is 0, then this side of this resistor is also 0 volts. And when we push the charge button, now we have 5 volts on one side and ground on the other. So we just have V equals IR. So the current is initially jumps to some large value, and the voltage at this point starts to integrate that current. So the voltage starts at 0, and we start to rise because we get some current. Well, I'm probably drawing that with the wrong slope already, but we didn't know that yet. So initially, we've got V equals IR. Now, let's say we wait a little bit of time. Now this voltage has been integrating that current. So this voltage is now, I don't know, 0.1 volts. So now there's only 4.9 volts across the resistor. So it's the current decreases because we've lost some of the voltage, the total voltage across the capacitor. And eventually we'll charge all the way up to 5 volts, and there'll be no more current because all of the voltage will be across the capacitor instead of being across the resistor. So that'll look like, okay, I draw that slope wrong. It's going to look like this kind of a curve. And so as the capacitor charges and charges, the voltage remaining across the resistor decreases, so we get less current, so it charges slower and slower. And this is what we call an RC curve. We've got an R and a C. And you're probably familiar with the shape of this curve from some kind of calculus class. This is a the e to the negative RT style curve. Okay, then let's say we push the discharge button. So that would be the discharge event. We instantly ground it, bam, and as soon as we let go, it would start to charge again. Now, the rate of time that it takes to do this is related to the values of R and C, because if R is really big, the overall current's small, so the capacitor might charge slowly. But if the capacitor is also small, then even a small amount of current will make it charge fast. So the ratio of R and C are going to be important to show us how long it takes for this to charge. So if we look at V out a little bit better here versus time, if we have a fixed value of C and we change the value of R, so if R is really small, it might take a very long time to charge. But if R is small, so we have big current, it might charge like instantly and then be like that. So this is like small r, and this is like big R for the same capacitor. The time that it takes to go from 0 volts to 2/3 of the final voltage has a specific name. That's called the rise time. So when the R is small, the rise time is short, and when R is big, the rise time is long. We should call this tau, and I'll give it the value of 1 over RC. This is also called, we will refer to this as the time constant of this particular circuit. So let's build this and take a look on our oscilloscope to see what it does. We'll take, so we'll do 5 volts, we'll go to our button, we'll go to our resistor, to our capacitor, to ground. We'll put a button across the capacitor, and I'm going to use a 1K and a 1 microfarad. And we're going to look at that point V out. So here's my end scope. And I'm going to take a red wire to get 5 volts into some row. And here's my charge button that goes to my 1K resistor. And then I'm going to find my 105 capacitor, which is a 1 microfarad. And it's going to go to ground. And then I need a wire to take a look at that on channel 1. Push that over here. And then I want my discharge button to go to ground as well. Okay, we'll switch over to the Enscope app. And so we see that the voltage is 0. It's been sitting there for a while. I can push the discharge button and nothing happens because that's just grounding the capacitor. Now I'm going to push my charge button. And okay, so it instantly jumped up to 5 volts. Now I've let go of the button and we see it's slowly discharging. Why would it be discharging? Well, the Enscope input has a resistor to ground. So that resistor is slowly stealing all of the charge off of the capacitor. So it's very slowly decaying towards 0. So I'll push my charge button again, instantly goes up to 5 volts. And then when I push my discharge button, instantly goes down. So I can go charge, discharge, charge, discharge, charge. And that is the natural decay due to my Enscope reading the voltage across the capacitor discharge. So I told you that this should have a characteristic shape, the RC curve. What's happening when I hit the charge button is it charges so fast we can't even see it. So we need to zoom in time to see that shape. So I'll choose 10 milliseconds. I'll ground my capacitor. I'll push the charge button. Oh, and we saw it so fast, but not long enough on the screen. I'll just discharge. I'll zoom in a little bit more in time, push the charge button, and I just missed the event. So the problem is that what the oscilloscope is doing is it's grabbing data, it's plotting it to the screen, and then it's grabbing more data, it's plotting it to the screen. But the actual time it takes to plot it is much longer than the data acquisition time. So normally we're just going to miss it. We're never going to see the event. It's just so unlikely that when we push the button, the scope was actually reading at that moment. So there's the ability of a scope called a trigger. So I'm going to turn trigger on. And the trigger says when the voltage in channel 1 goes from on a rising edge through the intersection of these two dashed lines, then we'll show the data. So what I'll do is I'll grab my trigger value and I'll move it up to, here's 2 volts. So when the voltage goes up through 2 volts, we will show the voltage. Of course, my scope crashed, so open it again. Okay, we're back to, say, 5 milliseconds, and we'll turn trigger on. I'm going to move it up to 2 volts. And I've pushed the discharge button, so I know my voltage is 0. Now I'm going to push my charge button. And the scope waited to save data until the red line went through that intersection to show me this plot. Now, if I turn trigger off, I can see what is the actual voltage right now, because once the trigger has happened, it will not show more data until that event happens again. So I'll push the discharge, I push the charge, push the discharge. So basically, I need to push discharge to know that the voltage is 0. Now I can turn my trigger on, and I can push the charge button. But it still missed it, so occasionally you'll miss it. So now I can push discharge, and I'll push charge, and it caught it. And I can push discharge, and I can push charge, and I got it again. It's going to have the same shape every time. I'd like to see it a little bit bigger, so I'm going to go to 1 millisecond. I'm going to push discharge, I'm going to push charge. It missed it, so I'm going to push discharge, now I'll push charge, and we see the curve. Now, unfortunately, this vertical line is fixed at that position. We can't move it back and forth. So if I wanted to see events that happened earlier than that intersection, I'd have to move my trigger value down, move it down to 1 volt. I'll push discharge, then I'll push charge. And now what I could try to do is I could try to get the amount of time it takes to go from 0 volts to 2/3 of the final 5 volts. So somewhere around here is the amount of time that it took to do that. And that is what we call the time constant, or it should be roughly 1 over RC. So in the lab, you'll be playing around with making these kinds of measurements. Let's do one more thing with this circuit. I'm going to take the buttons out. And we'll see, why do we want this kind of circuit involving a capacitor? Well, if we had just looked at this circuit instead, 5 volts to a button, to a resistor, to ground. So this is just a voltage divider, R1 and R2, where V out is some voltage depending on the ratio of R1 and R2. And we looked at that versus time. Well, when I pushed the button, it would go up to whatever that voltage was. And when I let go of the button, it would go back down to 0. When I replace R2 with a capacitor, now we don't have R2, what happens? That edge becomes rounded. So the capacitor here, because it takes time to charge, can smooth out sharp events like that edge. So this is what we call a filter. And we have a couple different types of filter. This first one, where we have V in, and then we have a resistor, and then a capacitor to ground, and V out is the voltage across the capacitor. This is called a low-pass filter. And we'll see in a second, what does that mean? It means that we keep low frequencies, we remove high frequencies. A high frequency is a sharp edge like this, so the low-pass filter can smooth out sharp peaks. So if we have kind of noisy data, let's see that this is the data we're interested in, but it's kind of like fuzzy. All that fuzzy stuff there, that's high frequency changes. So when we put that into our low pass filter, we should get out something smooth again. So to see what that does, I'm going to take the buttons out of my circuit, and I'm going to take A1 as a sine wave. And we'll go into the 1K resistor to the capacitor to ground. We'll see what A1 does on channel 1. We'll see what V out does on channel 2 to compare them. And at some point, I'll probably change this over to a triangle wave, just to see what happens. and we've got a 1K resistor and a 1 microfarad capacitor. Okay, so let's make those changes. So I've got a resistor from A1, the capacitor to ground. I'm going to put A1 onto channel 1 so I can see my input voltage, and I want to compare it to the output voltage, which is between the resistor and the capacitor. Put that on channel 2. And we'll switch back to Nscope. And in Nscope, I will turn on A1. And let's go to a bipolar. We'll go to a nice big sine wave. And we'll zoom in so that we see only a few peaks. Usually when we're looking at sine waves and things that change with time, we only want to see a few cycles per screen. So we'll keep adjusting our time scale to make that happen. Now I'll turn on channel 2. And they're right on top of each other. And let me increase the frequency of my signal. We'll go to 3 Hertz. Still on top of each other. We'll go to 13 Hertz. And then at this point, we get too many sine waves per screen, so we'll zoom in a little. And now they're still on top of each other, but it appears that there's a little phase lag. So the green is not quite in phase anymore. It's slightly either ahead or behind of the sine wave. And notice that every time that we grab the sine wave, we get in a different phase because the scope is just randomly sampling. So one thing I could do is I could say single every time I want one of these, and then it stops. Or I could leave it in continuous mode and turn the trigger on, and the trigger always grabs the data, in this case channel 1 on a rising edge, and always plots from that point. Let's go a little higher. We'll go to 30 Hertz, a little more phase lag. Go to 60 Hertz. Now we're starting to see something here. The input signal is red, does not change, but the output signal, the green, is now a little bit smaller. Let's go to 130 Hertz. Green is smaller even more. Let's zoom in a little bit. Let's go to 300 Hertz. Wow, suddenly the amplitude of the output is a lot smaller. Let's go to 1000 Hertz and then 3000 Hertz. So what's happening, as we increase the input frequency, the amplitude of the output wave gets smaller. And it will be your job to figure out how much smaller did it get and plot that versus frequency. And what you want to do is compare the peak to peak. So the red peak to peak here is something like 4 volts, and the green right now, the peak to peak, I want to zoom in on green just to get a better estimate. That's 500 millivolts from here to here. So this is almost 500 millivolts. So the 4 volts got turned into 500 millivolts. If we go back to 50 Hertz, put them on the same scale, zoom out in time. This is nearly the same as 4 volts and 4 volts pretty much. So we'll see the interesting shape of the curve. So the what we're looking at is a frequency versus magnitude plot. The magnitude of the output wave versus the frequency of the input wave. Initially, they're the same, so we call it 1. So if 1 volt comes in, 1 volt goes out. In this case, 4 volts went in and 4 volts came out. And as that frequency increases, I don't know, it does kind of like it falls. And it will be your job to figure out when does it start to fall, like at what frequency, and then how can we use that in future circuits to take an input, a noisy signal, and filter it to make a nice smooth signal, and how do we choose the R and the C? We'll be doing that a lot in the future labs, so this is just your first little brief introduction.